Hello, welcome to Fundamentals of Acoustics. Today is second day of the 6th week of this course, and we will continue the extension discussion we were having yesterday. Yesterday we had developed an expression for impedance in a closed tube. So, what we will do today is we will develop a similar expression for impedance but here the geometry we will consider will be for an open tube. So, impedance for an open tube. So, what is the condition in an open tube? So, that is the tube, this is the open end, this is my piston moving back and forth, x equals 0 at the open end, x equals minus L at the closed end. Just outside the open tube we have pressure, ambient pressure. So, P T is equal to P naught, and because of continuity, which means that just at a point inside also the pressure is going to be P T is equal to P naught, but P T is equal to P of x and t plus P naught, and if P T is P naught, which means that P at 0 and at all times is 0 pascals. So, that is the condition for an open tube. So, with this understanding we will develop an expression for impedance for an open tube. Now, so how do we do that? We start with these transmission line equations. So, P x t omega x t omega. So, here capital P and capital U are complex pressures and complex velocity, P plus P negative, P plus minus P negative over Z naught E minus j omega x over C, E j omega x over C, E j omega t. Now, we apply the boundary condition B C at x is equal to 0, which says that P is equal to 0. So, we take this second equation, which is actually the first equation. So, complex pressure is equal to P plus E minus j omega x over C plus P minus E j omega x over C E j omega t is equal to 0 at x is equal to 0. So, why do we say that complex pressure is also 0? Because the actual pressure is 0 and the complex pressure, the real part of complex pressure is the actual pressure. So, complex pressure also has to be 0. So, we put in this relation x is equal to 0. So, we get P plus P minus E j omega t equals 0, which means P negative equals minus of P positive. So, with that understanding we rewrite the transmission line equations. Rewriting transmission equations for open tube. So, what do we get? P x t omega u x t omega equals P plus minus of P plus over Z naught, and here also we get P plus over Z naught E minus j omega x over c E j omega x over c E j omega t. So, now we expand these relations. So, pressure omega equals P plus E minus j omega x over c plus E j omega x over c E j omega t, and velocity, complex velocity is so I should have put a negative here. So, this is P plus over Z naught E minus j omega x over c plus E j omega x over c E j omega t. So, if I simplify the terms in the brackets, what do I get? I get P plus times, so E minus j omega x over c minus E j omega x over c is minus 2j sin omega x over c, and then of course exponent to the power of exponent j omega t, and for the velocity relation I get P plus over Z naught, and the term in the parenthesis is 2 cosine omega x over c E j omega t. Now, impedance, specific acoustic impedance is what? It is defined as the amplitude of the complex pressure, and we write it as P x omega, and the amplitude of the complex velocity. So, let us identify what is the complex pressure amplitude for this thing. So, if I look at this term in circle, this term in circle represents the amplitude of this complex pressure. Why is it? Because the amplitude of exponent j omega t is 1. So, the amplitude of complex pressure will be whatever is there in the blue circle. Okay. So, in the numerator for the expression for Z, we will write P plus minus 2j sin omega x over c. Okay. Similarly, this term in green is the amplitude or complex pressure amplitude of velocity, because the amplitude of exponent of j omega t is 1. So, the complex pressure amplitude of u is P plus times 2 cosine omega x over c, and there is a z naught here which will come in the numerator. So, this 2 cancels out, P plus also cancels out, and what I am left with is minus j z naught tan omega x over c. Okay. So, Z for an open tube is minus j z naught tan omega x over c. So, that is the impedance for impedance. And what type of impedance it is? It is specific acoustic impedance for an open tube. Okay. So, again we can develop a plot for this also, and the graph will be somewhat different, but the value of this acoustic impedance again repeats itself after lambda distance, because each lambda distance corresponds to a phase difference of 2 pi. So, after every 2 pi value, when omega x over c becomes 2 pi, the value repeats itself. So, that is the second part. The third part we will discuss today is impedance for an infinitely long tube. Okay. So, if I have an infinitely long tube, and at one end of this infinitely long tube there is a piston which is exciting some sound, then the condition for such tube so P plus represents the amplitude of the wave travelling in the forward direction, and P negative represents a negative wave travelling after reflection, and because this is a tube which is infinitely long, P negative is 0. So, the transmission line equation for this one is P plus Z naught okay. So, if that is the case, then P of x t omega equals P plus E minus j omega x over c times E j omega t, and U x t omega is U plus E j omega x over c, oh excuse me, P plus divided by Z naught E j omega t. Okay. Now, once again this represents the complex pressure amplitude. So, I will write the expression Z is the ratio of P complex pressure amplitude divided by complex velocity amplitude, and that is equal to P plus E minus j omega x over c divided by, so the complex pressure velocity amplitude is this term in blue. So, that is P plus by z naught E minus j omega x over c, and that becomes simply Z naught. So, with this what we will do is summarize. So, you have a closed tube, then we have an open tube, and then we have a tube which is semi infinite, because we know its beginning where the sound source is getting the source is pushing air in and out. So, for closed tube Z of Z which depends on x and omega is J Z naught cotangent of omega x over c. For open tube, Z is equal to J, but it is negative Z naught tan omega x over c. And for semi-infinite tube, this is equal to Z naught and that is equal to rho naught c. So, one important observation is observations. The first observation is that Z x naught x comma omega, it does not depend on nature of excitation. What does that mean? What that means is, see, when we were calculating this value of Z x in all the three cases, I did not even specify what conditions exist due to piston, right. This is one boundary condition which is there. Okay. So, I did not, because the piston which is exciting the sound source, it generates some P plus, and when we calculate Z, this P plus cancels out, and this cancellation happens in case of infinitely long tube. It also happens in case of a tube which has a open end, right. P plus cancels out. So, the motion of the piston actually influences the nature of P plus, but P plus cancels out. So, whether this piston is moving at u, it has a velocity u, or it has a velocity something else, or it is producing a known pressure, it does not really matter. This P plus cancels out. Okay. And we see the same thing in case of closed tube also. I never defined any conditions at x is equal to minus L, because P plus cancels out. So, the Z naught, not Z naught, Z, it essentially depends whether the tube is closed or open, or it is infinitely long. This is one thing. Second, so pressure at a given point x a, at a given point and at a given point and time. So, at a given point and at an instant of time t1, let us call it, and velocity at the same point x a and at the same time, they are off by how much? By, so in case of they are off by, so let us write down these three things. So, if so they are off by, so the phase, so essentially they are off by 90 degrees in case of what? Closed tube, right, because which means that if u is at 0 degrees u, then pressure will be at 90 degrees, then only we will have this J component. Okay. Then they are off by negative 90 degrees in case of open tubes. So, if u is at 0 degrees, so these arrows, they do not depict the direction of u, they depict the phase. Okay. So, u is at 0 degrees, then pressure will be at minus 90 degrees. Okay. So, if u is at 10 degrees, then pressure will be at 100 degrees, and so on and so forth. Okay. And in case of infinitely long tube, what is the phase difference? it is 0 degrees in case of semi infinite tube. So, pressure is like this and so is pressure as well as velocity are having the same phase, okay. There is no phase difference. So, that is there. So, with this we will now close the discussion for today. What we have done is we have captured how pressure and velocity, they are related through this term called phase, and we have explored this relationship in context of open tubes, closed tubes and semi infinite tubes. So, tomorrow and day after tomorrow we will continue this discussion on Z, but in the next 2 days, at least in the next 2 days, we will do this discussion in context of imperfect terminations, where it is neither closed tube nor an open tube, but the situation is somewhere in between. So, that is what we will discuss in next 2-3 sessions. So, thank you and have a great day.